recording. Okay, so I've returned on the recording. Okay, so we start chapter 2. Probability of A is n squared over n from theorem 1.4. So we want to find the probability of events A. So chapter 2 is in combinatorial methods, which is a way of finding the values of n span and n. And so sometimes you need a counting procedure to find the values of n span and n. Okay, so the first counting procedure in 2.1 is the multiplication principle, and it can be used to count the number of ways of selecting one element for each of case sets. And so this is an example illustrating that. Okay, so here's a set A, which is equal to A1, A2, A3, and B is the sets B1, B2, B3, B4. Okay, so you can ask yourself a question. How many ways can you select one element from set A and then one element from set B? Okay, and so this is an example of the multiplication principle. Okay, well, so can someone tell me what you think the answer is? So how many ways can you select one element from set A and then one element from set B? So Brian guessed 24. I'm glad you guessed. It's not 24 though. 12, correct, Brian. Okay, so why is it 12? Right, 3 times 4. Okay, so there are 3 things in set A and 4 things in set 4. And so the number of ways to choose, you have 3 choices to choose something in set A, and you multiply 3 by the number of choices in set 4, in set B, which is 4. So the answer is the size of set A times the size of set B, and that's equal to 3 times 4, which is 12. So that's the number of ways to select one element from set A and then one element from set B. So make sure to mute. Okay, so if you participate or if you're not participating anymore, you have to mute your mic if you're done. Okay, so let's look at the whiteboard. So I'm just going to illustrate for you what's happening here. So if we draw this grid here, and we have 4 rows. Rows are horizontal, so I just drew 4 rows. And then there's 3 columns. So those are the 3 columns. And so if you have elements of the set B, which are B1, B2, B3, and B4, and you have elements of set A, which are A1, A2, and A3, then you can think of all the ways to choose an element in set A and an element in set B as being how many ordered pairs you can make from these things. So you have A1, B1, you have A2, B1, and you have A3, B1. You have A1, B2, you have A2, B2, and A3, B2. Okay, keep going. Okay, and so you have these ordered pairs. Okay, so so there are 12 possible ordered pairs you can make where the first member is either A1, A2, or A3, and then the second member is either B1, B2, B3, or B4. And so you can see that these 12 correspond with the 12 ways to choose an element, first an element in set A, and then an element in set B. Okay, so you add up, you count the number of boxes in this grid, and it's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or 3 times 4 is 12. Okay, so this is just illustrating the result we already got, that there are 12 choices. Okay, here's the next theorem. This is theorem 2.1. So let A1, A2, and so forth, AK, be sets consisting of N1, N2, up to and including N sub K elements respectively. What that means is that set A1 has N1 many elements, set A2 has N2 many elements, set A3 has N3 many elements, up to and including A sub K, set A sub K, which has N sub K many elements. Okay, so there's a correspondence between this list and this list. The order stays the same in that correspondence. Okay, there are N1 times N2 times ... times N sub K ways to select first an element from set A1, then an element from set A2, and so forth, up to including then an element from set A sub K. Okay, so this is just saying what your intuition would tell you, right? So this, in the case of K equals 2, this says that A1 is set A and A2 is set B. And so counting the number of ways to select first an element from set A1, then from set A2 is multiplying the number of elements in A1 times the number of elements in A2. That's the number of ways to select first an element in A1, then the element in A2. Okay, but this is for an arbitrary number of sets. So instead of having 2 sets, like in this example, you could have K many. So you could have 3, 4, 5, 6, 7, 8, 9, 1, 2, 1,000, 1,000,000, right? And so this theorem tells you how to count for any of those values of K. Okay, so example. So example 2.2. Mr. Levine has 5 jackets, 10 shirts, 6 ties, and 7 pairs of slacks. So part A, the question is, how many different outfits? With one of each possible. Okay, so it means outfits consist of 1 jacket, 1 shirt, 1 tie, and 1 pair of slacks. Okay, so how many different outfits with one of each are possible? Okay, so can someone tell me the answer to that? Correct. So Brian is 2 for 2. So Brian, why is it 2,100? Yeah. So, but I want more specific answers. So in this class, I don't always just want the answer. I want you to know how to apply the theorems that we discussed. So how does this how can we apply theorem 2.1 specifically to this example? What are the sets what are the A's in this example, and what are the N's, right? In this example, we have 4 sets, right? You have A1, A2, A3, and A4. So A1 is a set of 5 jackets, 5 different jackets. A2 is a set of 10 shirts. A3 is a set of 6 ties, and A4 is a set of 7 pairs of slacks, right? And N1 is 5, N2 is 10, N3 is 6, and N4 is 7, right? So we have the A sets, the A's from theorem 2.1, we have the N's from that theorem. And so from that theorem, the conclusion is that the number of different outfits, the number of ways to choose one element from each of those 4 sets or how many different outfits, choosing one jacket, one shirt, one tie, and one pair of slacks, right? That's multiplying n1 times n2 times n3 times n4. Okay, so you can see how you can translate this problem into the variables in theorem 2.1. And so when you translate all this information about outfits and jackets and shirts and ties and pairs of slacks into sets and the size of those sets, you can talk about the answers to this problem without talking about outfits, without talking about jackets, without talking about shirts. Okay, so you can apply this situation to a much more general one and get the answer that way. Okay, so this one very specific example of making outfits is part of a much larger, more general situation that theorem 2.1 describes. How many ways to select one element from each of K sets. Okay, so yeah, so the answer is 2100. So just to give that description, using the language of theorem 2.1, set A1 is the set of 5 different jackets. Right? The set A2 is the set of 10 different shirts. The set A3 is the set of 6 different ties. I'm just saying they're different so that because I want you to think of each of these things as different elements in a set, right? So we have 6 elements in that set, not 1. And then A4 is the 7 different pairs of slacks. So it's made up of those 7 different pairs of slacks. And so we have our 4 sets, A1, A2, A3, A4, and that means that N1, which is the size of A1, is 5. N2, which is the size of A2, is 10. N3, which is the size of A3, is 6. And N4, which is the size of A4, is 7. And so we now have, by theorem 2.1, we have that the number of ways, the number of different outfits is equal to the number of ways of selecting one element from each of the sets A1, A2, A3, and A4, right? And that's equal to N1 times N2 times N3 times N4. So even though this example is very simple, it's important to see how we get this answer using the theorem. Because when problems become more difficult, having already understood how to use this theorem in the simple one, you can understand how to use it in a more difficult problem. And then you can make a difficult problem easy by breaking it down in this way. Okay, so when you multiply that, you get 2100. The answer is 2100. Okay, so the number of different outfits is equal to the number of ways of selecting one element from each of the sets A1, A2, A3, and A4. That's equal to N1 times N2 times N3 times N4. That's equal to 5 times 10 times 6 times 7. And that's equal to 2100. And that's the answer. Okay, so that's part A, finding the number of outfits. Part B says if 2 jackets, 3 shirts, 2 ties, and 2 pairs of slacks are blue, what is the probability that a random selection will result in an all blue outfit? Okay, so if 2 jackets, 3 shirts, 2 ties, and 2 pairs of slacks are blue, what is the probability that a random selection will result in an all blue outfit? Okay, so let's introduce some notation. So we're going to let B equal the event of an all blue outfit. Okay, I wrote the words the event of an all blue outfit. You could have also just written blue outfit. Okay, you could have said B equals blue outfit. Now, B equals blue outfit means we both understand that this is an event and you're abbreviating, right? This is so that you understand what I'm doing. B is the event of an all blue outfit. This consists of all the outfits in which everything in the outfit is blue. So all the outfits where you have a blue jacket and a blue shirt and a blue tie and a blue pair of slacks. Okay. So you can abbreviate. You can cut short the naming of these events. But if you're confused by what an event is, you should write it out so you understand what you're doing. Okay, so let B equal the event of an all blue outfit, which is a blue outfit. Okay, which is blue outfit. Another way to say it shorter. Okay, so so now the question is, what is the probability that a random selection will result in an all blue outfit? So it's asking, what is the probability of this event B, right? B is the event of an all blue outfit. And the question is, what is the probability of an all blue outfit? So we want to find P of B. So P of B, using the terminology of our theorem, 1.4, right? P of B is equal to N sub B divided by capital N, where N sub B, the numerator, is the number of sample points in the event B. And capital N is the number of sample points in the sample space. Okay, I'm going to write extra things here to help you follow this. So N sub B is the number of sample points in the event B, right? This is what it always is. And capital N is the number of sample points in the sample space for this experiment, right? So we want a probability, right? So Kishan, you're saying the answer is 2 times 3 times 2 times 2, right? So the question is a probability. So this is, so it's not a terrible mistake because it's very easy divided by 2100, correct? So, but let me go through it. Okay, so so you have probability of an event B, which is N sub B over N, which is the number of sample points in the event B divided by the number of sample points in the sample space. Okay. Now, in this particular problem, that means that this is equal to the number of all blue outfits divided by the number of outfits, right? So the sample space consists of all the different outfits. And so the number of sample points in the sample space is the number of different outfits you can choose, right? So the denominator is the number of outfits. The numerator is the number of sample points in the event B. The event B is all blue outfits. So the event B consists of all the outfits in which everything is blue. And so the numerator is the number of all blue outfits. Okay, well, filling in what we already know, the easiest thing, the denominator, the number of outfits, that was part A. The number of different outfits is equal to 2100. So the denominator is 2100. The number of outfits is 2100. So the probability of getting an all blue outfit is the number of all blue outfits divided by the total number of outfits. Okay? Saying that each outfit you're equally likely to choose any outfit, then the number of all blue outfits divided by the total number of outfits is the probability of getting an all blue outfit. Okay, so we boiled the problem down to finding the number of all blue outfits, right? So we boiled the problem down to finding the number of all blue outfits. Then we just plug that number in above to get the probability of an all blue outfit. Okay. Okay, so the number of all blue outfits is equal to, well, just like before, you have 4 sets. You have the set of blue jackets, you have the set of blue shirts, you have the set of blue ties, and you have the set of blue pairs of slacks, right? So the set of blue jackets has 2 things in it. 2 blue jackets in it. The set of blue shirts has 3 blue shirts in it. The set of blue ties has 2 blue ties in it. And the set of blue pairs of slacks has 2 blue pairs of slacks in it. And so the number of all blue outfits is the number of ways of choosing one element from each of those sets. And that's 2 times 3 times 2 times 2. So the number of all blue outfits is equal to N1 times N2 times N3 times N4. This is reusing the notation from Theorem 1.4. Okay, so I'm reusing the n's to now mean the number of elements of blue jackets, blue shirts, blue ties, blue pairs of slacks, right? Okay, so before I used the n's to mean something else, and now I'm using it to mean this. Okay, so this is 2 times 3 times 2 times 2. And so that's equal to 24. Right? Okay, so that's what Kashan said. So there are 24 all blue outfits. And so you just put that in the numerator. And so it's 24 divided by 2100. Okay, and then you can simplify it. You can write it as a reduced fraction in the fraction simplest form. You can write it as a decimal. Okay. My personal preference as a mathematician is to think of fractions, not decimals, but you can use decimals too. Okay. Right, and so 24 over 2100 is equal to 0.0114. Okay, that's because I feel like fractions are more expressive of a quantity, right? Like 24 over 2100, I think looking at a fraction, you visualize the number better if you see it as a fraction as a decimal, right? 1/2, you think of it as 1/2, right? But 0.5 means 1/2. The decimal doesn't really represent the quantity as well as a fraction does. Okay. Okay, so that's 2.1, 2.2. 2.2 is on permutations. So definition. So we're now going to talk about another accounting procedure in which involves permutation. So first, let's define a permutation. Definition: a permutation of R elements is an ordered set of R elements. Okay, there is a first element, a second element, a third element, and so forth, up to including an rth element. Okay, the usual notation for a permutation of R elements is a list of the elements in the proper order enclosed by parentheses. Okay, so for example, the ordered pair 1, 3, 5, 1, 3, 5 in the parentheses is a permutation of 3 elements, where 1 is the first element, 3 is the second element, and 5 is the third element. Okay, so ordered, this notation gives added structure to just a set. When you have a set, you just have a collection of objects. When you have, this is called an ordered n tuple, or this is an ordered triple specifically because there's 3 components. When you have an ordered n tuple like this, with the parentheses, you don't just have 3 things. In this case, you have an ordering of them. Okay, so that's called having additional structure. Okay, but now having, in this case, an ordered triple, you include the order, and so this specific object that we're talking about includes the fact that we're assigning these things in order. So this order triple says that 1 is the first thing, 3 is the second thing, and 5 is the third thing. And so since an order triple tells you that information, if you change the order of the things in the order triple, you are no longer talking about the same order triple. So the order triple 1, 3, 5 is not equal to the order triple 3, 1, 5. Okay, even though they're the same 3 things are there, the order is changed. And so these are 2 different order triples. Okay, so these 2 are not equal because the arrangement is different. Okay. Okay, so one goal is to count the number of permutations, number of distinct permutations. Of R elements from a set of N elements. Okay, so if you have a set consisting of N elements, right? You may not have to list all the things in the set. You may be only looking at R of them and say, okay, how many ways can I take R of the things in that set of N elements and order them? Okay, and so that would be counting the number of distinct permutations of R elements from a set of N elements. So let's look at an example. So this is example 2.4. And so part A says list the permutations of 3 elements from the set. And the set is the set 1, 2, 3, 4 of 4 elements. Okay, so we want to list the permutations of 3 elements from the set 1, 2, 3, 4, 4 elements. So, for instance, you could have 1, 2, 3, right? You could have, I guess I'm going to put them next to each other because you could have 1, 2, 4. You could have you have 1, comma 3, comma 2. You could have sorry, let me start this list again. You have 1, 2, 3. You have 1, 3, 2. You could have 2, 1, 3. You could have 2, 3, 1. You could have 3, 1, 2. You have 3, 2, 1. You could have 1, 3, 4. You could have 1, 4, 3. You could have 3, 1, 4. You could have 3, 4, 1. You could have 4, 1, 3. You could have 1, 2, 4. You could have 1, 4, 2. You could have 2, 1, 4. You could have 2, 4, 1. You could have 4, 1, 2. You could have you could have 4, 2, 1. You could have 2, 3, 4. You have 2, 4, 3. You could have 3, 2, 4. 3, 4, 2. You could have 4, 2, 3. And you could have 4, 3, 2. Okay. And so those are all of the permutations of 3 elements from the set 1, 2, 3, 4, 4 elements. Okay, so there should be 24 here. 1, 2, 3, 4, 5, 6, 7, 8. See 23. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1. 3, 1, 2, 3, 2, 1, 3, 4, 1, 4, 3, 3, 4, 1, 4, 1, 3, 4, 3, 1. There we go. Now that's all of them. Very good. Okay. So wow, that's perfect. Okay, so we have 3 rows, 8 each. So 8, 16, 24. Okay, so these are all 24 of the ways to order 3 things in the set with 4 elements. Okay, so this is the list of all 24 distinct permutations of 3 elements from the set 1, 2, 3, 4 of 4 elements. All right. So part B is count the number of permutations of 3 elements from a set with 4 elements. Okay, I mean, we already have the answers 24 because of this list, but if we didn't want to list all 24, there's a way to calculate it without making that full list. So in order to do that, first you have to think, okay, what are the number of ways to choose a first element, right? So you want the number of permutations of 3 elements from a set with 4 elements. And so everything in this list is an ordered list of 3 things, right? So you have a first thing, that's the number, and so the number of choices is the number of ways to choose a first element. And you multiply that by the number of ways to choose a second element. And then you multiply that by the number of ways to choose a third element. Okay, so you have a certain number of choices for the first, then you have a certain number of choices for the second, and then you have a certain number of choices for the third. Well, the number of choices you have for the first element, since it's a set of 4 things, you have 4 choices for the first thing, any of the 4 elements of the set. But now you have to multiply it by 3, because the next thing you choose is different from the one you previously chose. There are 4 elements in the set. You have 4 choices for the first element, but now each thing is different. And so now there's only 3 left that are different from the first one you chose. So that's times 3. And then for the third choice, you've already chosen 2 and they were different. But if you had a set of 4 things, there's only 2 left that are different from the first 2 you chose. And so now you have 2 choices for the third. And so since you're talking about counting permutations of 3 elements, you stop at 3. You have 4 times 3 times 2, and that's equal to 24. And so without listing all 24, you could instead calculate the number 24 by this method. So no, it's not times 1, right? Because it's the number of permutations of 3 elements. Even though 4 times 3 times 2, okay, you get it. So even though multiplying by 1 gives you the same number, it's wrong in how you got the answer, right? So the way you get the answer is 4 times 3 times 2. Okay, good. Okay, so that's the key. That's one of the important points of the problem, that there's 3 elements, right? It's a number of distinct permutations of 3 elements. And so you stop at 4 times 3 times 2. Okay. All right, so that's an example of counting the number of distinct R permutations from a set with n elements. Here R is 3 and n is 4. Notation and definition. P, R, N denotes the number of distinct permutations of R elements that can be obtained from a set of n elements. P R N denotes the number of distinct permutations of R elements. Okay, I kind of wrote the same thing twice. PRN denotes the number of distinct permutations of R elements that can be obtained from a set of N elements. Okay. So this is theorem. Yes, Kashan. Okay, so don't raise your hand. Just speak. Okay.
So they have so there's 24 ways of doing permutations, right?
There are 24 3 permutations in the set with 4 elements. So this would correspond to P. So in this example, from example 2.4, we see that P 3, 4, which is equal to the number of 3 permutations in a set with 4 elements, is equal to 24. That's what you said, right?
Yeah.
Yeah. Okay, good. So P34 is number of 3 permutations, number of distinct 3 permutations in a set with 4 elements. So yeah. And so this number is always the same. And so if you're looking at a completely different problem, in the sense that they're talking about something completely different, but the answer is P34, that can happen. So, right, so this notation is a general notation that applies to infinitely many examples. And so you could be talking about one person can be talking about outfits, another person could be talking about something else completely different, and you could both describe the answer as P34 and you both be right. So so it's one of the strengths of probability, that you can replace the entire problem. You can replace the words and you can replace the real life situation with just mathematical notation, and you get the answer. Okay. So the answer to that problem is P34, which is 24. Okay. I just need to plug my my thing into the computer so we're not battery. Okay, so next is theorem 2.2. And so that theorem tells you the value of PRN. It's a formula, which as a student, you know, formulas when you're taking class is always great because you can just use it on a test and get the answer right, right? So PRN is equal to n times n minus 1 times n minus 2 times n minus 3 times ... That's multiplying. I always feel weird not putting the multiplication symbol in case students don't know what I mean. Then it's times ... times n minus r plus 1. And so this is for positive integers, r and n, with r less or equal to n. Okay, so there's some things that probably need to be explained, but first let me just say, right, so this is the formula. So if you're counting the number of R permutations in a set with n elements, that number is represented by this symbol. And so this symbol is getting more complicated. You used to have symbols like X and Y, right? Now we have a symbol P, lower script R, up superscript N. And so every part of this symbol is telling you something about the thing it represents. The P is for permutation, number of permutations. The lower script R is telling you you're talking about R permutations, and N is telling you how many total things there are in your overarching set. So PRN here is telling you it's the number of R permutations in a set with n elements. Okay, and so you can again think about this as multiplying choices, right? So let's go to the whiteboard. So this is the formula. And so if you're taking notes while I'm talking, make sure to write this down. PRN is equal to n times n minus 1 times n minus 2 times n minus 3 times ... times n minus r plus 1. The conditions are important for positive integers r and n with r less or equal to n. Okay, r cannot be greater than n. So r is less than or equal to n, and both r and n are positive integers. Okay, so on the whiteboard, I'm just going to illustrate how we get this formula. Okay, so again, the formula, I guess I'll write it again. So we have PRN is equal to n times n minus 1 times n minus 2 times dot 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 times n minus r plus 1. Okay, that's the formula. I'm going to write it one other way. It's equal to n times n minus 1 times n minus 2 times dot 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 times n minus r minus 1 in parentheses, right? When you subtract something in parentheses, you distribute the minus sign when you get rid of the parentheses. So n minus parentheses r minus 1 becomes n minus r minus negative 1, which is n minus r plus 1. So that's why you get this weird plus 1 at the end, because you're subtracting n minus r minus 1. You're subtracting r minus 1. That's why you have a plus 1 here. Okay? And so if you have a set with r things in it. So you have a set with n things in it, and you want to count the number of ways of choosing r of them, right? So here, this n here, right? This n is corresponding to the fact that the size of the set is n. Okay, so there are n things in the set. Let's say this is one example. And then the r, right, is denoting the fact of how many things you want to choose from the set. So you have a first thing you choose, the first thing you choose, the second thing you choose, the third thing you choose, and then up to and including the last thing, which is the rth thing you choose, right? So when you choose the first thing, you have n choices, right? So you have n choices for the first thing because you have a set with n things in it. You could choose any of those n. So your first choice, you have n options. That corresponds with the n here. For the next thing, you've already chosen 1. So you have n minus 1 remaining to choose for the second thing. That's the n minus 1 here. And remember before, by the multiplication principle, you just multiply the number of choices, right? So it's n times n minus 1. So you would multiply this number. Now, for the third thing, you've chosen 2 already, and you said it's n things. So you have n minus 2 choices for the third thing. And you would again multiply that number, and you keep going. So you keep multiplying. And then when you get to the last thing is the rth thing, not the nth thing. So the last thing is the rth thing. So each time you have one less thing to choose. So the first time you chose, you had all n. The second time you chose, you had n minus 1 choices. The third time you had n minus 2. So you can see that there's a correspondence between the thing you subtract and the choice number, right? So the first choice was n minus 0. The second choice was n minus 1. The third choice was n minus 2. So the number you subtract is always this positive number you're subtracting from it is always 1 less than this, right? First, n minus 0. Second, n minus 1. Third, n minus 2. And so can someone tell me the number of choices you have for the rth thing then? It's n minus, and then in the parentheses, what do I put? When it was 1, when it was the first, it was n minus 0. When it was the second, it was n minus 1. When it was the third, it was n minus 2. So for the rth, it's n minus r minus 1. I'll leave, good, you're right. So it's n minus parentheses r minus 1. So that's the number of choices you have for the rth one. And so that's why the last thing here in this product is not n minus r. It's n minus parentheses r minus 1. And when you distribute the minus sign, you get n minus r plus 1. That's why this product has this weird final term, n minus r plus 1. It's really n minus parentheses r minus 1. And that corresponds with the number of choices you had for the last thing here. This was for this one, right? Okay, and so that's why this is why you have this symbol represents this product, the number of r permutations in a set with n elements is equal to this product given by this symbol. Okay, that makes sense? Okay, so you might want to look at that again. Okay, but R has to be at most n, where R and n are positive integers, right? Because if you have a set with n things, you can only choose at most n things, right? R cannot be greater than n. You can't ask how many ways can I choose 10 things from a set with 5 elements in it, right? You only choose at most the number of things in the set. So R has to be at most n, right? So R has to be at most n. And n is the number of things in the element in the set. And as we just care about n being positive integer, and R, the number of things you choose, we're also saying that's positive. And so both R and n belong to the set of positive integers. This symbol represents the positive integers. Z looks subscript plus. That's a set of positive integers. Okay. This set is the set 1, 2, 3, 4, and so forth. Okay, that's a set of positive integers. This epsilon means R and n are elements of that set. Okay, this is shorthand. R n epsilon z plus is shorthand for both n, R and n are positive integers. They're both elements of this set. Okay. So in example 2. This theorem 2.2, we have that's the value of PRN, the number of R permutations in a set with n elements. Next is corollary. What's it doing? Good. Okay. Okay. So we have corollary 2.1. So corollary 2.1 says that P lower script R superscript R is equal to, well, now you want the number of R permutations in a set with R elements. It says it's R times R minus 1 times R minus 2 times ... times ... times, and then following the notation, it's R minus R plus 1. Instead of n minus R plus 1, it's R minus R plus 1 because n is R, but R minus R plus 1 is 1. So this is really R times R minus 1 times R minus 2 times ... times ... times 1. And that's equal to R factorial. And this is for positive integers R. Okay, and so just notation and definition. For positive integers, n factorial is equal to n times n minus 1 times n minus 2. We're going to drop the multiplication sign, but this still be multiplied, times up to including 1. Okay, and 0 factorial is equal to 1. Okay, so this is by definition. 0 factorial is equal to 1. N factorial in general is equal to the product of the positive integers from n going down by 1 each time to 1. So, for instance, 3 factorial is 3 times 2 times 1. Okay, n, that symbol is pronounced n factorial. Okay, so that symbol is known by n factorial. Okay, so example 2.5. A club has 100 members, president, a vice president, a secretary, and a treasurer are to be selected from the membership. All members are eligible, but can only hold one office. Okay, so A is find the number of distinct choices of officers. Okay, so how many ways are there to choose a president, a vice president, secretary, and a treasurer from this club with 100 members where everyone is eligible, but everyone can only hold at most one office? You can't have someone be both the president and vice president. Okay, so the answer is just the number of distinct choices of officers is equal to, well, you have 100 choices for who could be president. That's times then 99, the number of remaining people you can choose to be vice president, times 98, the number of remaining people to choose for secretary, because there's 2 less people, and then times 97, which is the number of people remaining that you can choose for treasurer, because you've already chosen a president, vice president, and secretary. There's 3 people out of the 100 that have already been chosen to hold an office, and so there's 100 minus 3, which is 97 remaining people for the 4th choice. So you multiply those 4 numbers, and you get 94,109,400. Now, another way to think of it is that this is also, you could also just go directly to the notation. So if you translate this in terms of permutations, then what you want is the number of 4 permutations in a set with 100 elements. You want the number of ways to order 4 things in a set with 100 elements in it. Okay? Because you want to choose a president, a vice president, a secretary, and a treasurer out of 100 people. And so how many ways can you make lists of 4 people using from a set with 100 things in it? Okay? And so you'd have the set of ordered 4 tuples where each component is a distinct element of the set with 100 different members in it. Okay, so that's P400. And so you get that number. Okay, so probably the best way to do this problem is to say, okay, the number of distinct choice of officers is this, actually you say 100 P4. So 100 P4. So the number of distinct choice of officers is 100 P4. And then once I've done that, you just calculate it using the formula and you get 94,109,400. So if you understand the notation, then by translating the problem into mathematical notation, it's very easy to get the answer. Okay, and so part B is, what is the probability Mr. Lee, Miss Jones, Mr. Williams, and Miss Schwartz will be selected as president, vice president, secretary, and treasurer, respectively. Okay, so 4 people from those 100, one of them his name is Mr. Lee, another person is named Miss Jones, another person is named Mr. Williams, another main person is named Miss Schwartz. Those are 4 specific people from the 100. And so there's only one way that you can choose Mr. Lee to be president, Miss Jones to be vice president, Mr. Williams as secretary, and Miss Schwartz as treasurer. So we're just going to again introduce some notation. So let A equal the event of Mr. Lee, Miss Jones, Mr. Williams, and Miss Schwartz being selected to be president, vice president, secretary, and treasurer, respectively. I'm just writing everything out. Okay, so let A equal the event of Mr. Lee, Miss Jones, Mr. Williams, and Miss Schwartz being selected to be president, vice president, secretary, and treasurer, respectively. Okay, so the problem is asking, what is the probability of that event? What's the probability that that happens? Well, so that's n sub a divided by capital N. So this students have trouble with this one, and I understand why. It's an easy problem that you can overthink. That it's easier to overthink the problem than to think correctly, right? So this event in which Mr. Lee is president, Ms. Jones vice president, Mr. Williams secretary, Mr. Schwartz is treasurer, there's only one way that can happen. So this event only consists of one sample point. So n sub a is 1. Very easy. Capital N is the number of 4 permutations in a set with 100 elements, or 100p4. And that's 94,109,400. And so when you got the answer to part A, the answer to part B is just 1 over that number, because there's only one out of the 94,109,400 ways to choose a president, vice president, secretary, and treasurer. Only one of those ways are in which Mr. Lee is the president, Ms. Jones is vice president, Mr. Williams is secretary, and Ms. Schwartz is treasurer. So the probability of it happening is 1 over 94,109,400. Okay, and then as a decimal, that's equal to 0.106 times 10 to the negative 7th power. Okay, so it's extremely, extremely unlikely that that would happen. Okay, and so that is the end of 2.2, which is on permutations. Okay, so I don't know if you can see the I have to put this on. Okay, so homework 2 is on 1.4.5 and on 2.2. And so we just finished 2.2. So I'm now going to assign homework 2. Okay, so let's go back. So I'm now assigning homework 2 to be due. Today is Tuesday, so I'll have it due next Tuesday. So this is going to be due Tuesday, September 28th. At the start of class. Okay, I'm not collecting it, right? We're just for you to do it and have questions about it at the start of class. Okay, so that's when it's due. I say, Cesar, answer your question. Homework 2 to be due Tuesday, September 28th, at the start of class. Okay. Okay, so I've now assigned it. Okay, so the homework is, you look here, 1.4.5 and 2.2.2. Okay, so we've now gone over the material you need for that homework. So Friday is the only Friday is the scheduled office hour day. So I've said if you can't make an office hour, I can meet with you another time, right? If you can make the office hour Friday, it would be better to do it then, right? But if you can't make it on Friday, I can meet with you another time. Okay, ask me about that right after class. I have to leave right after this class ends for another class, but immediately after the class, you can, if you need to talk to me about that, you can, or you can email me about it if you want. But if you email me about it, you have to email me in advance, not right before. Okay, the schedule for another day maybe. Okay, so that's end of 2.2. 2.3, combinations. The binomial coefficient. So 2.3 is on combinations, and specifically the binomial coefficient. So let's start with the definition. Okay, so a combination of R elements is an unordered set of R elements. We use the notation A1, comma A2, comma dot dot dot, comma A sub R to designate a combination of the elements A1, A2, and so forth up to including A sub R. Okay, so a combination of R elements is an unordered set of R elements. So here, we don't care about order. So a combination of R elements is just choosing R things in any order, right? If you're playing a game of cards and somebody handed you 2 cards, like handed you 5 cards, like in poker, you don't need to know what poker is. Somebody just gives you 5 cards, and the cards you're holding are your hand, and the order doesn't matter. So an example of having hands in poker is an example of a combination of R elements. You have 5 cards. Each card is different. It doesn't matter the order you were given the cards. They're now just your cards. So that would be an example of a combination of R elements. Okay, it's an unordered set of R elements. You have R things, and there's no order to them. Okay, and so we use the set notation, the set containing those R things, A1, A2, up to including AR, to designate a combination of those elements. Because what a set tells you is just the things you have, and it does not assign order. Okay, a set says less than an ordered pair would, or triple, or an ordered n tuple. It's just telling you the things you have. Okay, so that's a notation for a combination of R elements. And so from this definition, you can see that the combination 1, 3, 5, meaning you have the numbers 1, 3, and 5, is equal to the combination 3, 1, 5, where before the permutations were different. Here, the combinations are the same, right? The ordered triple 1, 3, 5 does not equal the ordered triple 3, 1, 5, because an ordered triple is an assignment of assigns order to the things you have, but a combination doesn't do that. Okay, so having a 1, 3, and 5 is the same as having a 3, 1, 5. Those two combinations are equal. So another question you can ask is what are the number of distinct combinations of R elements from a set with n elements? And so here's the answer. The number of distinct combinations of R elements from a set with n elements is equal to NCR. R is the subscript, N is the superscript. That's read N. This is read NCR. N for the superscript, then C, then R. You read it from top to bottom. So this is NCR in words. So NCR is the number of distinct combinations of R elements from a set with n elements. And then another notation for it, which is better. And so this is the one you should use, is this one, where there's no C, but you just have, it looks like that. So this is a better notation. It's easier to write. This is much harder to write. This is more expressive of what you're doing, because you're talking about a number of combinations. So C represents combinations, right? And you're saying that there's n things in the set, and you want the number of R combinations. Okay, but this is the better notation because it's easier to write. It takes less time. This is also called a binomial coefficient. Okay, so the number, I just moved this down. It's saying the number of distinct combinations of R elements from a set with n elements equals NCR, which is equal, this is another notation, and that's equal to a binomial coefficient. So this is an example of a binomial coefficient. The reason it's called a binomial coefficient is because you can see from this equation, if you take A plus B and you raise it to the nth power, this is equal to the sum. After FOILing out, you'd say A plus B times A plus B times A plus B times dot 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 times A plus B, where there's n of them in the product. The way you can get that product is by FOILing out, right? Multiplying, taking each choice of products, and then you add them up, so that you can write this in succinctly as the sum from R equals 0 to n of NCR times A raised to the n minus R times B to the R. Okay, and this looks very hard to understand. It's not that difficult once you see it. I'm just going to write the same thing, but using the other notation. This is the usual way to write it. Usually, instead of writing NCR here, you would write it like that. So this would be the more common way to see this. And it's much easier to read the right one than the left one. This is much easier to see on the page than this. Okay, so this is it's called a binomial coefficient because it's a coefficient of this sum. Okay, so these are, of course, these are coefficients in this sum. Okay, this sum is a sum of products, and you have a constant in front of products, a certain number of A's times a certain number of B's, and there's a number in front, and those numbers are coefficients. This is called the binomial coefficient. Okay, so an example of the note would be if you took x plus y and you cubed it, right? Then what that would be, it would be x cubed plus x squared times y, but it wouldn't just be x squared times y. It would be 3x squared y. And then it would be plus 3x y squared. And then it would be plus y cubed. Okay. Now, you could get this by foiling. If you did x plus y cubed, it would equal to x plus y times x plus y times x plus y. And if you just FOIL that out, you would see that you would get an x cubed. You would get a yx squared. You would get a another instead of, I'm going to put x in front and then the y's after it every time, even though, so you have a plus xy squared. You have a plus x squared y. You'd have eventually another plus x squared y. You have another plus x squared y. You would have a plus x y squared. You have a plus x y squared. You would have a plus x y squared. And you would have a plus y cubed, right? And so if you add common terms, this becomes equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. So x plus y cubed is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. And you can see that by FOILing. Now, another way to do that is by using this formula, where x and y are a and b, and n is 3. And so using the formula instead, we get that x plus y cubed is equal to the sum from r equals 0 to n, where n is 3, of NCR, and choose R, you could also say, times A, which A is x, right? So this is x to the n, well, that's 3 minus R times y to the R power. And so this is equal to, when R is 0, oh, and the NCR is 3CR, because the exponent is 3, so it's 3CR. So what happens when R is 0, you get so when R is 0, you get 3C0 times x cubed times y to the 0, which is 1. Then plus, when R is 1, you get 3C1 times, when R is 1, you get x squared times y to the first, which is y. Plus, when R is 2, you get 3C2 times x to the 3 minus 2, which is x to the first, which is x, y to the r, which is now 2, so y squared, and plus, when r is 3, you have 3c3. And so when r is 3, x to the 3 minus 3 is x to 0, which is 1, and you have y to the r, which is 3. So you get this sum. And so then this is equal to 3c0. So computations, class is going to end any second now. I'm just going to quickly do this. If you have the combination 3c0, okay, I didn't tell you how to calculate this yet. I'll just tell you 3c0 is equal to 1. Next class we'll talk more about this. 3c1 is equal to 3. 3c2 is equal to 3, and 3c3 is equal to 1. Okay, so okay, and so those are the coefficients, and so the 1, 3, 3, 1 are the coefficients here. So this formula, these values here are coefficients in the final polynomial, and so that's why it's also given the name a binomial coefficient. Okay, that's what I want to say. So next class we will see examples of combinations and have a formula for how to compute numbers of combinations. Okay, so we'll have a further discussion as well as other things. Okay, as well as other things. Okay, so and don't forget the homework is due Tuesday, next Tuesday. So assigned homework 2, we do Tuesday, September 20th, the start of class. Okay, so we'll stop here, and that's it for today. I'm now